In this screencast, we're going to study work and how we use line integrals to get work in all dimensions. The idea is if you've got some curve moving through the plane, and that curve moves through a vector field, and the vector field has vectors of some sort. They're doing something. How do you calculate the work if you're not moving on a straight line and the vectors aren't constant? The idea before was that work is force times displacement, or we can do it in vector form as work is force dot the displacement vector. But that only works if the force is constant and the displacement's in a straight line. Well, here, it's not straight. We're not moving in a straight line. And the vectors, notice they're changing as we move throughout. Just a picture of that. Your vectors could be swirling around, and maybe you're moving in a circle. You're not moving in a straight line, and you're not. The vector field is not constant. So the idea, if I want to actually calculate work, then I need to do something else. The idea, we take our curve. The way you solve most problems in mathematics is you take a curve and you break it up into a bunch of little bits. Along each tiny bit, it's almost a straight line. And the forces don't change very much. So the idea is a little bit of work is found by taking your force times a little displacement. So in order to find that displacement, the idea is I'm moving along a curve. I need a direction. The direction we're moving is t, and the length we've traveled is ds. So this little displacement is really the tangent vector, and I need a magnitude, which is ds. So a little bit of work is really your force times the tangent vector dotted with the tangent vector times ds, which means if you want a total amount of work done, it's add up f dot t ds. I'm going to integrate along the curve C. So we need to simplify that. How do you get t? Well, we already know the unit tangent vector is found by computing r prime and dividing by the magnitude of r prime. We also know ds is found by computing r prime dt. Notice something nice happens and the magnitudes cancel, which means this is really just integrate along the curve f dot r prime dt. This is the key equation we're going to use to get work. It can be simplified, and mathematicians often like, and not just mathematicians, but people like to write less if possible. The idea is dr dt is the same thing as r prime. So if I took the dt up and put it over here, then I could replace this, and I could just write f dot dr, and where dr really means find r prime times by dt. So here's our working formula. There's another way that people often write this. And if you have a vector field, and the vector field is given by an m, an n, and a p, it's in 3 dimensions. This is just the name of the first, second, and third variables. And your curve is always given by your x, y, and z variable. Then dr, well, that's just dx, dy, dz. Then the idea is I need to take f times it by dr, which means work is equal to, let's dot these, m dx plus n dy plus p dz. This is an alternate formula for getting work. You're going to see it written in 3 different ways, but every single one of these 3 ways all requires you parameterize a curve, and you eventually have to use this formula up here. Let's now take a specific example. We'll go into 2 dimensions. Let's let our vector field be the spiraling vector field, the counterclockwise rotation. The vectors are causing things to spin counterclockwise. And so here is our vector field. It's actually the vector field I drew over here. Let's take a curve, r of t, and let's just use a circle. Let's use a circle of radius 3. So we've got 3 cosine t, 3 sine t, and t should go from 0 to 2 pi. I want to find the work done by f as I move along this curve. So I want the work done by f over the curve, which is a circle of radius 3, and we're going to move counterclockwise. So the key idea is I need to find r prime. That's what this formula up here says. R prime is negative 3 sine t, 3 cosine t. And now, work is take f and dot it with our prime. So I just need to dot these. So negative y times negative 3 sine t plus x times 3 cosine t dt, and then I need to integrate from 0 to 2 pi. Now I need to know what x and y are, and remember those always come from your parameterization. So I can replace the y with 3 sine t, and I've got another negative 3 sine t. X is the x coordinate in our r, so that's 3 cosine t, 3 cosine t dt. Now notice that this is a 9 sine squared plus a 9 cosine squared, which really means it's 9 times sine squared plus cosine squared, or 1. So this is really just integrating 9 dt from 0 to 2 pi. You can integrate it as 9t, or I just want to remind you of the fact we could now think of it as an area, and we're going to go from 0 to 2 pi. The height is 9, so really we're just trying to find that area. It's 9 times 2 pi, which is 18 pi. That completes the screen.